This program has been made possible by a grant from the UCF Office of Research and Commercialization.
The UCF Office of Research and Commercialization is committed to moving the discoveries of our faculty and students from ideas to innovation to realization. By moving research from the laboratory to the private sector, we are helping to diversify Florida's economy and helping to bring high-paying jobs to our state. This program presents some examples of our research and our efforts to transition this research to the private sector.
Welcome to another edition of Zenith, the program about research. I'm your host, Ed Hyland, and today we'll hear from the inventor of a revolutionary process that may one day lead to medicines being produced cheaply and in great quantities by growing them inside plants. Plus, the curse of dementia, how a UCF project is helping patients. These stories and much more coming up here on Zenith. The mission of the Office of Technology Transfer at the University of Central Florida is to proactively facilitate the transfer of technology from the university to the commercial sector through enlightened technology transfer policies, processes that efficiently and effectively reduce off-the-shelf technology inventory, and dedication to customers and being easy to do business with. Our guiding principles are development of intellectual property assets, licensing them into the commercial sector, which leads to a return on investment for the university. We envision an eventual contribution to the economic development within the Central Florida region, the state, and the nation. UCF will be recognized as a contributor and leader in the future economic performance of the Central Florida region. Alzheimer's and other conditions rob brain function. There is no cure or even an effective treatment right now, but a research program under the guidance of UCF is helping those with dementia to retain memory and maintain their ability to stay active.
Hold your arm back and go forward. Hard. Yes.
You are seeing part of Brain Fitness. Brain Fitness is a unique, innovative program in which persons that have been diagnosed with either early loss of memory, you may know it as dementia or Alzheimer's disease or another type of dementia.
Hop. Hop. Bunny.
Bunnies.
Bunnies.
Rabbits.
Rabbits.
Bugs.
Yeah. Bugs. Bugs. Like crickets. Swing your arm back. Go forward. Hard.
They come twice a week for it to have mental and physical stimulation.
Hey, all right.
There you go.
Another aspect of the program is that students in the Department of Communication Sciences and Disorders also come on Friday mornings, and they provide one-on-one mental stimulation for the participants.
I've realized that although there's a lot of patterns in dementia and there's a lot of characteristics that they share, doing these activities every week with them, their consistency does pay off.
Yeah, we learned something by it, and they are good. They are good. Can't complain about one of them.
How long would it take you to make one?
This has been such an exciting program. It started out with the vision of one woman whose husband was diagnosed with a type of dementia very early in his 50s. It's hard for you to do things,
It's
but...
hard for me to,
And then it's gone.
and it's gone.
Right. The words are gone.
Yes.
The words are gone. And it was her vision and her hope to have something that he could go to be mentally and physically stimulated. But when we go back to music,
Yep.
all the tunes are still up there.
You got it.
That's right. I'm very thankful, very excited to bring students here because they're really seeing that people can live with Alzheimer's disease. It's not a death sentence. It's something that you can learn to learn new strategies, new ways, how to dance around a conversation, to still stay socially involved with family and with friends.
Okay, I still get a number. Now, which one do you think?
The Brain Fitness program is funded through grants and private donations. A local church provides the space for free. We now turn to groundbreaking research that could lead to new ways to create, manufacture, and deliver vaccines. Perhaps most amazing is that it involves cultivating the vaccines within plants. Dr. Henry Daniell has been developing this groundbreaking research toward his goal of finding a treatment or cure to the top 10 diseases affecting humans.
There are a number of reasons. The number one reason would be the shortage. Every time we talk about flu vaccine shortage, and so plants can be produced in massive quantities, and therefore when a vaccine is produced in plants, there is no opportunity for shortage because it could be as abundant as food. So that is number one. And number two, there are problems with the current vaccine, the way it is produced. They are grown in eggs, as you pointed out, are cell cultures and yeast, viral culture and all that. These culturing systems require machines called fermenters. And these fermenters in the US are $700 or $900 million to build, and it has to be operated in a very sophisticated manner. And therefore, the cost of these vaccines are humongous. And many of the vaccines that are available are not affordable for many countries or people around the world. And we are talking of a population where 2 billion, 1/3 of the population is earning less than $2 a day. So the cost is not affordable. And thirdly, this technology is so old. The one that we are using is as old as Louis Pasteur's, and there are lots of disadvantages with that. The efficacy, for example, the cholera vaccine is effective not in adults, and in children the immunity is lost just in 2 years. And you have heard of the anthrax vaccine and so on, where the current system there is a toxin contamination and so on. So producing in plants make them clean, and therefore it can never cause the disease. And so there are several advantages to the plant system.
Before we get into the machinery, if you will, to make that happen, you focused, as I recall, with corn. You've used carrots, I believe, in some of your research, tobacco plants, and lettuce. Are those just favorites, or are they just because of the way that they grow so rapidly, for example?
There are reasons for choosing each system. We initially started off with tobacco because tobacco grows so abundantly. 1 acre of tobacco can produce 40 metric tons of biomass, and therefore we showed that we could produce entire required US vaccine for anthrax in 1 acre of tobacco. So the production capacity of tobacco is very high. However, tobacco has nicotine. Even though we did nicotine-free tobacco varieties, it will be very difficult to convince FDA that there is no nicotine in this, and therefore vaccines produced in tobacco have to be extracted, purified and injected. So that doesn't allow oral delivery of the vaccines unless you're a baseball player and chew tobacco. It's not feasible. Therefore, we developed oral delivery systems like carrot and lettuce, where the plants can be dried, powdered, and then made into capsules. And the cost between injectable and oral is tremendous. You're talking of pennies to hundreds of dollars per dose.
Well, let's focus then on the products or produce, I guess you should say, that we're working on here. So you're working with lettuce. What do you do to the lettuce to begin the process of actually developing a vaccine within the plant itself?
For each vaccine, in the traditional way, the pathogen, the virus or bacteria, is somehow killed or made less virulent, and then it is injected. That's the current system.
A weakened vaccine, a weakened form of it, sure.
Vaccine. And the downside of that is that there's always one virus or bacterium which is not weakened, and therefore that can cause the disease. The way we do this is we don't use any pathogen, weakened or not, at all. Instead, we only use the proteins that are necessary to stimulate the immune system to develop immunity. Therefore, the very first step then is we clone that gene that is necessary to make the protein. And in some cases, we may need more than one protein. For example, for malaria, we use 2. So we clone the gene, and then somehow we have to get this into the plant genome so that that gene permanently becomes part of the plant genome and will start producing this protein forever and ever. And almost 20 years ago, when I was at Harvard, our collaborators at Cornell came up with this machine that can shoot dice. And it's called a gene gun. And so as luck would have it, I was at Harvard. They were playing with this at Cornell. So I drove up to Cornell and then said, hey, we can shoot genes. We can shoot DNA. And that's how we came up with the technology of blasting these genes into the cells so that the cells would get these genes, and then it will forever and ever become part of the genome.
Now, do you have to do this for each individual plant? You mentioned earlier how much vaccine could be produced from one particular acre of plants, but I guess I'm envisioning having to inject each of the individual plants to make that happen.
Very good question. No, the answer is no. We have to do this for only one plant. And once we make that one plant, and then we grow that plant, collect seeds. In case of tobacco, a single plant produces 1 million seeds. So these seeds will forever and ever carry those genes. So the very first time when we do it, we do a few plants. But then once we get the seeds, we never have to do it again, because this has become permanent part of the genome. And we do all the tests to confirm that this is there forever and ever, and the genes are inherited to the next generation. We test them by growing up the seeds and looking for the vaccine production. So once we do that, then the scale up is the seeds. So this is the one that we'll be handing over to the pharma company to grow them up and then to produce the vaccine.
All right, so you have the plants, they have been injected, and they are producing the vaccine. The next step would obviously be what do you have to do to make sure that you can get it to a point where a human can ingest it?
Correct. 2 ways. If it is injectable, if you want to stick with the current approved system of FDA, then we extract these proteins, just as it's done for the current vaccines. You extract and then you purify it. FDA requires 99.9 percentile, and then no side effects, no allergy, all of these things, and then we can inject it. But the downside to that system is that the extraction process is the most expensive process. Usually 90% of the vaccine cost of production is the extraction. Once you extract it, you have to put it in the cold, refrigerate it, transport it, and so for remote part of the world, the villages where they have no refrigeration, they cannot have it. So the other method that we have developed is oral delivery. So we don't have to extract it. We just freeze dry these leaves and store. Once you freeze dry them, you can store them in the shelf, and we have tested this for a few years. The vaccine stays put. It's not degraded. Then we just powder them, very fine powder, fill it into a capsule, and then those capsules are then given as oral delivery.
So like the old pharmacist, you literally grind it up, if you will, powder it, and then you can figure out your dosages from there. We are not the first people to make the oral vaccine, the polio, for example. Oral polio vaccine is what we all had. So oral vaccine is incredibly more powerful than injectable vaccine. But because the polio was somehow 1 in 200 or 250,000 people got polio, simply because, as I said, 1 or 2 viruses live, and therefore it causes the disease. That was the reason that was pulled out, not because the oral delivery system was not good. Oral delivery system is more powerful than the injectable And it's
system.
not destroyed by the digestive tract.
Very good question, very good question. So you hit on the most important point. Several people who tried this oral vaccine, earlier when the whole virus or bacteria was orally given, they were still protected because they are cells. And when we make this refined vaccine with 1 or 2 proteins, when it's orally given, it gets degraded. Whereas this is where our technology comes in. We express it inside plant cells. So the plant cell protects the protein, the cell wall. So we call it bioencapsulation, but it's just a capsule by itself, even before we put it into a capsule. And so this protects it from the digestive enzymes and the acid and everything else. But then when the plant cells move through the intestinal system to the gut, bacteria in all of our gut system, bacteria live there. So they need some amino acids. So they chew up these plant cells and then get their amino acids. In that process, poke holes. And so the protein is released there. And that's where the immune system, gut immune system, is ready to grab them. And so our system overcomes the limitation of the oral delivery that's currently available. So this is the only system where this can be orally given and yet not destroyed in the stomach.
Let's talk a little bit about, in the remaining time we have, kind of where you stand, because you've been developing different vaccines over time. One of the first that I recall was insulin. Where does that stand? Is it being tried in humans yet, as far as the testing process?
Yeah. For insulin, we developed this not to just lower the blood sugar levels, but this immune system in the gut. We were able to actually prevent the onset of diabetes. In other words, it's a cure for diabetes.
A preventative, or?
It prevents. It forever blocks people getting diabetes, meaning in our case we developed it with animal studies. And again, the way the diabetes oral delivery works is that insulin-dependent diabetes is an autoimmune disorder. The body misunderstands its own insulin, attacks it and destroys it. So when we developed this insulin inside a plant cell and then gave to the gut immune system, it recognized the mistake and corrected it. So it no longer attacked the insulin, and then the body started producing naturally insulin. So this was done in diabetic mice. Where do we stand now? Yeah, we have published this a couple of years ago. And we have done subsequently, earlier when we published, we did studies with 50 animals and so on. Now scientists always want to recheck it and reconfirm it, so we've done it over 100 animals. We got even more fantastic results. And so we have gone and then looked at some of the side effects, if there is any, and all of that are needed before we go and file for human clinical studies. And that's where we are now, but the challenge is who is going to pay for the clinical trials, which is, in the US, it's about $100 million. So we really are looking for partners and investors who can jump in, because if they are interested in a cure and saving hundreds and millions of lives, this is the way to do it. And so they need to make the investment and then develop the product. So we have done preclinical studies, but we are still waiting for big investors or donors to move this forward.
And that's one of the challenges too, is that this is a methodology that produces cheap vaccine. There may not be as much profit in it.
That
for
is
pharmaceutical
an absolutely critical challenge that I am facing. I explained to you that my goal is to make low-cost vaccines. Insulin in the U.S., $20 billion of insulin is sold, insulin-related products is sold every year. I mean, you can imagine the world global market about this. If I tell them that you don't need insulin anymore, and then ask them to invest $100 million, it kind of contradictory. But I truly believe in my goal. I really want to have low-cost vaccines or low-cost biopharmaceuticals and develop cure. I don't believe that people should be injecting themselves. And even more outrageous, I will use the word, I'm sorry to use that, is that the current treatment doesn't give the full insulin that is needed. There are 3 chains or 3 proteins needed that naturally is produced. The insulin technology was developed in the 1970s, and scientists didn't know how to make 3 proteins. So they could make 1 by 1, and then they are combined and then injected. They never knew how to make 3. And so the 3rd chain, which is called a C-peptide, is never given to people who are taking insulin. And this has profound long-term consequences. Neuropathy, nephropathy, all the diabetic complications are associated. Several of them now we find out. So when we cure it, we have now shown that it produces all 3 peptides. So it's not that the current technology is perfect. We have limitations in that, and so we have to find a better way to do it.
We'll have more with Dr. Daniell in next month's program, including a first look at his latest breakthrough, an experimental vaccine combining treatments for cholera and malaria. This month's program is nearing an end, but we always leave just enough time for our Research Minute.
What it is, maybe it's just, or maybe it's a vaccine.
If we have problems with this normal process of cells dying, we have disease. What we're trying to do in our lab is to use what we know about how apoptosis normally happens in a cell and try to figure out how we can develop what we call a biologic, a treatment based on the biology of these BCL2 and BAX proteins that we can use to cause apoptosis in a cancer cell. We're trying to design the BAX peptides not only to kill cells, but made to also prevent cells from dying. Remember, one of the variants that we designed doesn't cause cell death at all. So why would we want to do that? Well, as I said, there's a number of diseases where you have too much cell death occurring. Heart failure, Parkinson's, stroke, Alzheimer's, autoimmune diseases, these are all examples where cells are dying when we don't want them to die. We might be able to design a version of the BAX peptide that can be protective and protect these cells from undergoing cell death.
The goal of research is to better understand the world around us. Our goal is to be a window to that world. Until next time, on Zenith, I'm Ed Highland.